Hello, everybody. Welcome to the third event of the Sustainable Chemistry Lecture Series. This time again, we have two excellent speakers. So let's welcome the third event of the Sustainable Chemistry Lecture Series. This time again, is the audio okay? I'm sorry, I have to interrupt.
It's okay.
Because I hear my echo. Okay, sorry. So this time again, we have two excellent guest speakers, and it's my pleasure to welcome Paolo Melchiorre from the ICIQ in Tarragona, and he will take us on a journey into the world of asymmetric photocatalysis. And our second guest is Schmelker from the University of California in Santa Barbara, and he will show us his work on new materials for energy conversion applications. And before we start with the scientific program, I would like to announce the next event of the SCLS series. As you can see here, it will take place on the 21st of April 21 at 4 p.m. Central European time. Here you can see the link. As usual, you need to register before you can enter the meeting, and you can find this link also on the website of the European Chemical Society. So these are the two guests, Professor Anja Mudring from Stockholm University in Sweden, and she will talk about using ionic liquids as transformative tools in material synthesis. And the second guest is Johan Martens from the Catholic University in Leuven, and he will talk about production, storage, and transportation of solar hydrogen, so a very important current topic. So I hope to see you all again there. I would like to finish my introduction with thanking the European Chemical Society and the KVCV, the Royal Flemish Chemical Society, for their support, for supporting our lecture series. And in particular, I would like to thank Thomas Franken from the KVCV for his tremendous support in organizing these events. Now I would like to hand over to Xiaobik, who is going to introduce our first speaker. Xiaobik?
Yeah. Yes. So it's my great pleasure to introduce Professor Paolo Melchiorre, an exciting chemist for the excited state. So, of course, it's quite obvious that I'll start with a brief introduction. So Paolo actually studied in University of Bologna in Italy. He finished his master's in 1999 and then started his PhD in the same university. In 2003, he finished his PhD and started his postdoctoral research in the same university. And in 2006, he finished his postdoctoral research and straight away started as an assistant professor. Since 2009, he is the research professor and senior group leader in ICIQ Tarragona in Spain, where he is currently working. It's quite obvious that he has won numerous awards. So some of the names I'm going to tell because I don't want to take too much time from his lecture. So very important one is Giacomo Simasian Gold Medal of the Italian Chemical Society, the Liebig Lectureship Award, Thieme Journal Prize. He has also won Young Talented Lecturer at ICIQ in 2011. He has become the Fellow of the Royal Society of Chemistry in 2020. He has won this Giorgio Modena Medal from the Italian Chemical Society, also Thieme Lecture from Germany, and Prize for Scientific Excellence from the Royal Spanish Chemical Society. Since 2019, he's the associate editor of Chemical Science, a flagship journal from Royal Society of Chemistry. So with this note, Paolo, I would like to invite you, and we are very much looking forward to your excited state chemistry.
Good afternoon, everyone. Sorry, I could not unmute myself. It is a real pleasure to be with you. Thank you very much for the invitation to be part of this lecture series event. I think it's very important during these difficult times we found ways for sharing our passion for chemistry, for science. So for me, really, it's great to be here today and to present some of the chemistry that we developed in my laboratories here at the ICIQ. I also like very much the topic, that is sustainable chemistry. What we are trying to do in our laboratories is to develop electroselective methodologies triggered by visible light for making chiral molecules. And when I start talking about photochemistry, I need to acknowledge this gentleman here, Giacomo Chamichan, Chami-chan was an Italian chemist, and he is considered the pioneer of synthetic photochemistry. This is a quite famous picture, probably the majority of you have already seen it, and that it was taken more than a century ago in Bologna downtown, the University of Bologna, where Chami-chan was doing research. And you see that he was performing many reactions on the rooftop of the chemistry building using the power of sunlight for making, for triggering these transformations. I have a sort of link with this picture, and since I was educated at the University of Bologna, in this very same building, I could not go to the balcony because it is not there any longer. Anyway, of course, today the chemistry department is called after Giacomo Chami-chan, and I was educated in that department. This is, of course, not the only reason why I like photochemistry. I like photochemistry mainly because it can unlock reactivities and allow reactions that would be extremely difficult to be achieved using classical ground state chemistry. So why so? In a simplistic way, we can say that when a molecule can be excited with a photon of, when it can absorb a photon of light, what we are doing is that you can promote one of the electrons in a low energy orbital into a higher energy orbital. And now in this new excited configuration, this molecule behaves in a completely different way from a point of view of reactivity and also from physical point of view. For example, an excited state molecule is at the same time a better reductant and a better oxidant than in the ground state. And this new reactivity acquired in the excited state will be the basis for the chemistry that we'll discuss today. So in the excited state molecules can start doing electron transfer chemistry to promote the formation of radicals, and the target for us was to use this mechanism in an antiselective catalysis. So the target that we are using for developing an antiselective catalytic strategies and making chiral molecules is organocatalysis. This is an established field of research that I would say was born 20 years ago. The target of organocatalysis is to use simple, small chiral organic molecules as catalysts to drive an antiselective transformations. Those two reactions, both of them published in 2000, conceptualized the field of organocatalysis as, let's say, a field of research. There were many other previous examples of organocatalytic reactions, but again, those two reactions in some way conceptualized the organocatalysis as a unique field. The first example is an important transformation, and a classical transformation in organic chemistry, an aldol reaction that was published by List, Lerner, and Barbas using a simple proteinogenic amino acids, proline. What is doing proline here? It is activating the carbonyl compound through the formation of this covalent intermediate that is an enamine that is nucleophilic and can trap different electrophiles, for example, and aldehydes. The same year, David Macmillan introduced the concept of iminium ion activation of alpha-beta unsaturated carbonyl compounds, again using a chiral amine, in this case to drive the formation of an iminium ion. In the ground state, this intermediate is a strong electrophile that can drive pericyclic reactions, such as in this case, or can trap nucleophiles to forge a stereogenic center at the beta position. Now, over the last 20 years, enamine and iminium ion catalysis has been extensively used by the synthetic community to develop many asymmetric transformations. The general perception, however, is that today is rather difficult to use the classical ground state polar chemistry of organocatalysis to develop other reactions. So the main question is in which way it could be possible to further expand the potential of organocatalysis in chiral molecule synthesis. Well, it is here where photochemistry can come into play, because the ability to shine light over a classical chiral organocatalytic intermediates and to switch on new catalytic functions can really open up opportunities for the design of photochemical asymmetric reactions that could not be achieved using, let's say, organocatalysis in the ground state. That was the target of my research group over the last few years, let's say 6-7 years. And that was to understand and exploit the excited state reactivity and the photochemistry of classical organocatalytic intermediates. So the first intermediate we focused on was an enamine. The enamine is known since a very long time. It is known that it is a strong nucleophile thanks to the pioneering studies by Gilbert Stokes that dates back to the 60s of the last century. Now, an enamine is a nucleophile and can trap a lot of electrophiles. If you have a chiral amine, of course, you can also control the stereochemistry of the stereogenic center. We have found, however, recently that enamines have also a rich photochemistry. In particular, we found that enamines are electron-rich compounds that can aggregate with specific electron-poor alkyl halides. And this aggregation brings about the formation of a new aggregate in the ground state. This is a new species, since those two compounds are sharing the orbitals to form new molecular orbitals. And this aggregation is called electron donor receptor complex. Now, the main peculiarity of an EDA complex is that it is associated, a charge transfer band that is associated to an electron transfer that sometimes lies in the visible frequency region. And this is exactly what happened with the enamine-based EDA complex. This compound was colored, could absorb visible light, that induced an electron transfer, leading to the formation of a radical, and then we could do chemistry with this radical that was not achievable, let's say, when using enamine chemistry in the dark. You may wonder how we figured out of the possibility for the enamine to engage in the formation of photoactive enamine-based EDA complex. Well, it was really an experimental observation, a visual observation of my students in the lab. Those vials contains all the reactants, the substrates, and the catalyst of the reaction they were studying with the enamines, and you see all of them are colorless. This is the reaction mixture. When you mix everything together, the enamine and the alkyl halides, the solution turns to bright yellow color. Why? Because we are generating in the ground state this enamine-based EDA complex that indeed can absorb in the visible frequency regions where the individual components absolutely cannot absorb. So here, conceptually, there is nothing novel, because the EDA complex theory was conceptualized by this gentleman here, Robert Mulliken, as far as in the 1950 of the last century. It is interesting for me to consider anyway that the idea for Mulliken to come up with EDA complex theory was really an experimental observation. Indeed, it is not so uncommon for a chemist, for a scientist, to observe that when you bring together some colorless compounds, sometimes you observe formation of a colored solution. This is exactly what happened to us as well. So what we could do with this enamine-based photochemistry? So we could develop this enantioselective alkylation of aldehyde using electron-poor alkyl halides, such as dinitrobenzyl bromide, phenacyl bromide derivatives, and those bromomalonate derivatives. We needed a chiral amine because we wanted to activate the aldehyde through formation of an enamine, but more importantly, here we needed light. Blue LEDs or 400 nanometer light irradiation in the dark. This chemistry was not proceeding at all. So this is not classical ground state polar chemistry. This is photochemical radical process. About the mechanism. Again, the main role is played by the electron-rich enamine that is colorless, that can aggregate with those specific electron-poor alkyl halide that are colorless too, to form a photoactive enamine-based EDA complex. Then you can shine light over this EDA complex to induce an electron transfer, leading to this radical ion pair. I told you that EDA complexes are known since a long time, but they have found very limited application in synthetic chemistry. And the main reason is the back electron transfer, which restores this ground state EDA complex, and of course is not synthetically productive. But in our case, upon the formation of the radical ion pair, we had a very good leaving group in the radical anion, the bromide, that could split to fight the back electron transfer and leading to the productive formation of this radical that then could be used for making the chiral molecule in the stereogenic center here. Over the time, recently, many other research groups over the world have identified and have many other strategies based on the photochemistry of EDA complexes to develop important synthetic transformations. So it seems that this strategy that is based on light, let's say activation, can be very useful also in synthetic chemistry. Anyway, going back to the mechanism of our reaction, what we believe that is happening is that upon the photoinduced electron transfer, this radical anion transpire out of the solvent cage. Then upon fragmentation, we have the formation of the radical that is intercepted by the ground state chiral enamine to force the stereogenic center. We generate this alpha amino radical that is a good reducing agent, can give an electron to a new molecule of the substrate to liberate this iminium ion that hydrolyzes to give the final product. This single electron transfer also regenerate this radical anion. So this means that in every catalytic cycle, we are regenerating this radical, and this is indeed a radical chain propagation mechanism. This is fully consonant with the fact that we measure the quantum yield of the overall process that is about 25. This roughly indicates that for any photons absorbed by the enamine-base EDA complex, at least 25 molecules of the final products are generated. So here, the photochemistry of the EDA complex serves as a sort of initiation that kicks in the first radical in this radical chain propagation cycle. The next target for us was trying to identify other organocatalytic intermediates that could engage in EDA complex formation. That means other type of intermediates other than enamines. And we focused on enolates, since they are electron-rich compounds that are electronically similar to enamines. More importantly, there are different organocatalytic strategies that allow for the preparation of chiral enolates under very mild conditions. For example, you can take this cyclic beta-keto ester. This proton in this position is rather acidic. You can use a base, cesium carbonate, the protonate, to form this enolate. If you do this in the presence of this phase transfer catalyst, this quaternary ammonium salt derived from a silicon alkaloid, that of course is chiral, you can form a chiral enolate. Our idea was that in the presence of an electron-poor substrate that is prone to EDA complex formation, such as perfluoralkyl iodide, we could indeed generate a colored EDA complex. And this is what we observed experimentally again. When putting all the substrates together, the colorless compounds turned to a bright yellow solution. Shining visible light over this enolate-based EDA complex, we induced the reductive cleavage of the carbon-iodine bond, leading to the formation of this perfluoralkyl radical that could be trapped by this chiral enolate to force this quaternary carbon stereocenter. Again, here in the dark, we had no reaction at all. So this was really a photochemical and antiselective perfluoralkylation process. We needed to work a little bit over the best catalyst to induce high stereo control. This was the best catalyst finally. And you see that we could trap different type of perfluoralkyl fragments. Using this strategy, also trifluoromethyl radical could be intercepted with high stereo selectivity using this enolate-based EDA complex chemistry. Next, we try to look for other donor compounds other than enamines that could engage in EDA complex formation with electron-poor alkyl halides. And in particular, we focus on indoles. It is indeed quite clear that the indoles resembles electronically the enamines. It is electron-rich. In principle, it can form an EDA complex. If you shine light over the EDA complex, you induce the formation of these two radicals in close proximity. The net reaction will be the alkylation of the indole at the two carbon atom. Now, from a synthetic point of view, this is not a reaction that is unique because you can achieve the same transformation in many other ways, for example, using Palladium Catalysis. What was interesting for us is that for the first time, at least in our lab, we could use a stable donor for the EDA complex formation. In this case, both the indole and also the other component, the alkyl halide, were stable substrates, while in our previous studies, we always generated EDA complex using transiently generated catalytic intermediates. So it was extremely difficult to characterize the EDA complex. The use of indoles allowed us to try to characterize this photoactive EDA complex. We were successful mainly thanks to Sandeep, one of my postdoctoral fellows at the time, that was able to grow crystals suitable for X-ray analysis of this photoactive EDA complex generated upon aggregation between the 3-methyl indole that you see here and the 2,4-dinitro benzyl bromide. So the interplanar distance between the two aromatic moieties is shorter than the van der Waals radii. This indicates that here we have an attractive force that brings together those two moieties. This is really a photoactive EDA complex that we could really see. And I was very pleased with these results because finally we could really see this interaction. This is at the basis, let's say, of the photochemical process. Now, moving on from this study, we learned that the indoles are electron-rich enough to engage in EDA complex formation. Recently, we tried to build upon this knowledge to come up with a sort of chemoselective functionalization of tryptophan-containing peptides. In particular, the idea was that the indole nucleus within tryptophan can engage in EDA complex formation with an electron-poor Katrinsky salt that is known to engage in EDA complex formation. There is different studies, such as, for example, this one by Frank Grolius demonstrating the feasibility of this interaction. And then, shining light over this EDA complex, we should generate an alkyl radical coming from this fragment of the Katrinsky salt that could promote, by proximity, let's say, the functionalization, selective functionalization of the tryptophan at the 2 position of the indole nucleus. This was the idea. We started with a simple dipeptide containing these tryptophan fragments as a simple model substrate in the presence of this peculiar or specific Katrinsky salt. And indeed, we observed by absorption spectroscopy that when you mix together those 2 substrates, we observe a new absorption band associated to the electron transfer. Using very simple conditions, a simple light illumination in the presence of a water mixture of a solvent and in the presence of a base, we could selectively functionalize the 2 positions of the tryptophan derivatives. This is true for many other aminoacidic residues, always in dipeptides. You can see that the alkylation happens exclusively at the indole nucleus, also in the presence, for example, of tyrosine or other type of aminoacidic residues, such as, for example, histidine or also serine, such as in this case. Now we are trying also to expand a little bit the applicability of this sort of bioconjugation. Please allow me to call this ways, of course, a little bit stretch, because still we could do a selective functionalization of tryptophan in tetrapeptides or tripeptides. Now we are trying, in collaboration, also to move to much more complex systems, such as, for example, in proteins. Anyway, in this case, we are just using visible light excitation of this EDA complex that is formed within the tryptophan aminoacidic residue to drive this radical functionalization at the tryptophan position. Okay, so everything started for our EDA complex photochemistry based on this study, the enantioselective alkylation of aldehydes. Now I would like you to focus on the results that we obtained with these peculiar substrates with the bromomalonate as radical precursors. Also in this case, the chemistry worked fine and we needed 400 nanometer illumination for the reaction in order to proceed. In the dark, there was no reaction at all. The problem was that we could not observe any EDA complex formation on bringing together enamines and bromomalonates. So the main question was, what is the photochemical mechanism here that allows us to generate radicals? And we didn't know that. So we started with simple mechanistic studies on this specific reaction between butanol bromomalonate in the presence of this chiral amino catalyst that is classically used for enamine catalysis. This chemistry required at least 400 nanometer, of course, or below frequencies, but 400 nanometer was enough for this reaction to proceed. Absorption spectroscopic studies, however, clearly indicate that all the individual components of the reaction and the catalyst could not absorb at 400 nanometer. The blue line is the reaction mixture. So the main question was, what is this transient intermediate that we are generating during the process that can absorb at 400 nanometer? And we started to believe that was the enamine itself. To make sure of this possibility, one of my PhD students at the time, Mattia, that now started his independent career in Nottingham University, isolated this enamine, and he could confirm that this compound can absorb till 420 nanometer. More importantly, using a laser, we could excite the enamine and observe the emission from the excited enamine. And this allowed us to perform Stern-Volmer quenching studies with the bromomalonate, and we did observe quenching. That indicates that there is an interaction between the excited state of the enamine and the ground state of the bromomalonate. Based on that, this is the mechanism that we propose. In this case, we are using a completely different photochemical mechanism available to enamine to generate radicals. In particular, the enamine can absorb light, and this excitation turns a simple nucleophilic compound into a strong photoreductant in the excited state. With this new excited state reactivity now, we can activate the bromomalonate that otherwise would be inert to the ground state nucleophilicity of the enamine, and we can activate this compound through single electron reduction. And this leads, upon fragmentation of the carbon halogen bond, to the formation of the radical. Then we go back to the ground state regime. The ground state chiral enamine trap the radical to set the stereogenic center. This alpha amino radical can abstract the bromine atom from a new substrate to regenerate this carbon-centered radical. This intermediate is unstable, can collapse, leading to the final product and to the catalyst. Also here, we are in the presence of a radical chain propagation mechanism because we are regenerating in every step a carbon-centered radical. So we have found that enamines have also rich photochemistry. And enamines have two different mechanisms available, photochemical mechanisms, to generate radicals. And those mechanisms can be useful then for triggering enantioselective photochemical radical processes that would be impossible, let's say, when using enamine chemistry in the dark. Okay. The next target was try to study the possibility of using iminium ions in the excited states. Iminium ion is the other very general activation mode in organocatalysis that is characterized by a strong electrophilicity. And this electrophilicity can be used to trap different nucleophiles to force a beta stereosensor. What we learned, however, again by experimental observation, is that when you mix together classical substrates for iminium ion formation, such as cinnamaldehyde and this commercially available catalyst, what you observe is that colorless substrates turn to bright yellow coloration. Why? Because the iminium ion can indeed absorb in the visible region. This should not be a surprise if you think that the ability of iminium ions to absorb visible light is really at the basis of the mechanism of visions for all the vertebrates. But we don't want to induce any EZ isomerization here. The target was to use the excited state reactivity of iminium ions to develop new photochemical asymmetric processes. The main problem was to predict which type of reactivity expecting from an excited iminium ion. And to do so, we capitalized upon our previous studies on the excitation of enamines that I just briefly mentioned before. Now, an enamine in the ground state is an electron donor. This electron donicity is magnified upon excitation, and this is why the enamine in the excited state becomes a strong single electron reductant that can activate electron-poor alkyl bromide through single electron transfer. In contrast, the iminium ion is an electron-poor substrate in the ground state. Upon excitation, it should become extremely eager to get an electron. That means it will become a strong oxidant. So in this case, what you need to use as the redox couple is an electron-rich substrate that can give an electron to the excited iminium ion, leading to the formation of this radical. And hopefully then you can use this radical to develop an enantioselective radical process. The point was to identify a suitable compound of this type that can exchange electrons with the excited iminium ion. Again, it was Mattia, that I mentioned also before, that came up with the suggestion of using a benzyl silane. Now, this compound is stable, commercially available, is not too difficult to be oxidized, and upon excitation, it is known that the silicon group can split in a reversible way, leading to the productive formation of a benzyl radical. So we found a model reaction to test the feasibility of the excitation of iminium ions. Mixing together cinnamaldehyde, benzyl silane in the presence of a chiolamine, because we want to generate the iminium ion. And then the most important of the reagent, we use a purple LED for the selective excitation of the iminium ion. In the dark, this process is not possible for the simple reason that the organic silane is not nucleophilic enough to attack this position of the electrophilic iminium ion. So we used commercially available catalysts, and the initial results were interesting because these catalysts afforded very good chemical yield with low stereoselectivity. Again, no light, no reaction at all. While this pronylol system, this catalyst, provided much better level of stereo control. The problem was the chemical yield. We thought to improve this chemical yield in a short time, but we were wrong because we could not get better than 30–35% of chemical yield. But finally, my students identified the problem. And here, the problem was the oxidation potential of the amino catalyst that was similar to the oxidation potential of the organosilane. Now, upon the strongly oxidizing condition of the photoexcited iminium ion chemistry, it is possible to oxidize the catalyst to form this extremely unstable radical cation that can start a lot of different degradation pathways. So the target for us was to make this catalyst more resistant toward oxidation. It was one of my postdoctoral fellow, Yannick, that came up, I think, with a very good idea that was to introduce in this pyrrolidine scaffold this difluorinated moiety, this geminal difluorinated moiety that increased the oxidation potential of the amino moiety. This made this compound much more stable, and it could perform catalysis in a much better way in terms of chemical yield and enantioselectivity. We also try to increase the level of enantioselectivity by modifying the stevic hindrance of the catalyst, but you see, we put, I don't know how many fluorine atoms just to get a couple of points more of enantioselectivity. So this is the catalyst of choice in our enantioselective photochemical process with iminium ions. What we can do with this chemistry, we could include a benzyl group in the different cinnamaldehyde derivatives. The limitation is that if you use an aliphatic substituent on the alpha-beta unsaturated aldehydes, we shut down completely the photochemistry and the chemistry is not working. We could also use different type of organic silants as radical precursors. The mechanism, the main role is played by the excited iminium ion, that is a strong oxidant, can take out an electron from the organic silane. This leads to the formation of this radical. The single electron transfer also leads to the formation of this 5-pi electron system. This can be considered a sort of persistent radical because this is a benzylic position and also allylic position, so it's kinetically rather stable, and this chiral radical can govern a radical-radical coupling to force this beta stereocenter. Some evidence to support this mechanism comes from Stervolmer quenching studies. We observe the emission from the excited iminium ion that could be quenched by the presence of the benzyl side. And this is a good backup for the single electron transfer that we believe is the key for the formation of the radicals. We extended this chemistry to other type of radical precursors, for example, with organic silants bearing an heteroatom in the alpha position, such as a sulfur, a nitrogen, or an oxygen, and you can introduce this scaffold at the beta position of cinnamaldehyde with high stereo control. There are other organic radical precursors that we can use, such as trifluoroborazoles or dihydropyridines, such as in this case. And we can generate isopropyl radical, but also many other secondary carbon radicals, and we could intercept them at the beta position of cinnamaldehyde. We estimated that in the excited state, the iminium ion is really a strong oxidant with an oxidation potential of about 2.2, 2.3 volt. That means we could also activate functionalities that are extremely difficult to be activated or to be reacted under classical polar reactivity, such as, for example, an olefin of this type. But in this case, we can take out an electron from this olefin to form this distonic radical cation. If you place a carboxylic moiety, you can drive a cyclization leading to this tertiary radical that is prone to radical-radical coupling. We can make this compound through a sort of enantioselective radical cascade process. The excited iminium ion can also activate, through oxidation, of course, this cyclopropanol. This former radical cation opens up very quickly for strain relief, leading to the formation of this tertiary radical, again, radical-radical coupling to set the first stereogenic center. We also generate this nucleophilic ground state enamine that is primed for intramolecular aldolization, leading to the formation of this cyclopentanol, having 3 contiguous stereogenic centers with very high stereo control. I told you that the excited iminium ion is really a strong oxidant. We can also activate toluene. Now, toluene is a solvent. In principle, it should be inert. But here, the excitation of the iminium ion can really drive the oxidation of toluene, leading to this radical cation, which magnifies the acidity of this benzylic proton. Upon the protonation, we have the formation of this radical-radical coupling. We can make this chiral molecule starting from cinnamaldehyde using a feedstock chemicals, an organic catalyst, and purple light. I would say that it would be not easy to develop the same transformations using the iminium ion chemistry in the ground state. And this is a sort of demonstration that indeed the excited state reactivity acquired upon light excitation can really be useful for developing strategies, asymmetric strategies, not possible under classical thermal conditions. But of course, this idea of drawing out new reactivity profiles by photoexcitation is not limited to organocatalytic intermediates. You can also think to excite other organic molecules with an established profile in the thermal chemistry, such as, for example, the Manchester. This is known to be an hydride delivery system, so you can reduce, for example, microreceptors. But this was found already in the 80s, but also recently by other colleagues, of course, that Manchester can also be excited upon light absorption. And in the excited state, this compound becomes a strong single electron reductant, pretty much similar to the enamines that we have discussed before. And now with this excited state reactivity, you can activate electron poor alkyl bromides through single electron transfer for M-forming radicals. Our idea, based on these studies, is that we could generate these 4 alkyl dihydropyridines. You see that this compound is structurally very similar to the Manchester, so we believe that upon light absorption and excitation, this excited molecule should behave in a very similar way. That means it should become a strong single electron reductant. Upon single electron transfer, we will generate this radical cation here that is known to be unstable and should collapse, leading to the formation of this alkyl radical. So if this is true, the excitation of 4-alkyl dihydropyridine should bring to a dual reactivity behavior in the excited state, because this compound should behave at the same time as a radical source and also as a pool of electrons. This was an idea of Luca Buzzetti, one of my PhD students at the time, who synthesized this benzyl dihydropyridine, and indeed this compound could be excited at 400 nanometer, 405 nanometer, and could engage in electron transfer chemistry. We also made sure by EPR spectroscopy, of course, upon irradiation, that this compound could generate benzyl radicals. So it was a source of benzyl radicals. And then we tried to use this dual reactivity behavior in the excited state, again, the ability to donate radicals and donate electrons at the same time, to develop a little bit more complex chemical processes. In particular, we focused on nickel cross-coupling. In the last few years, the last 5-6 years, the combination of photoredox catalysis and nickel cross-coupling has attracted a lot of interest, mainly because the photoredox catalyst is able to generate radicals that are essential for the nickel cross-coupling mechanism, and also to turn over the nickel catalyst through single electron reduction. In principle, here we have a compound, the dihydropyridines, that upon excitation can do both jobs, can turn over the nickel catalyst to reduction, and can also offer the formation of radicals. So what we tried to do was to develop a nickel cross-coupling chemistry without the need of an external photoredox catalyst, just relying on the excitation of the dihydropyridines. And I'll try to explain the idea behind this. So this compound can absorb light, and in the excited state can become a strong single electron reductant. In the very first step of the reaction, a sequential single electron transfer will bring the nickel 2 pre-catalyst into the active nickel 0 catalyst. In the meanwhile, we also generate this radical cation that can collapse, leading to the formation of an alkyl radical. The nickel 0 at this point can trap the alkyl radical to form this nickel 1 intermediate. It is prone to oxidative addition with the aryl bromide, leading to this nickel 3 intermediate. At this point, the reductive elimination will force the carbon-carbon bond within the cross-coupling product. And here it comes the problem, because this nickel 1 intermediate is inactive. There is not much of a problem if you think that the excited dihydropyridine is a strong reductant that can give an electron to the nickel 1, bring it back to the active nickel 0, regenerating the alkyl radical, and this chemistry can keep going. Indeed, it was possible to develop this photochemical nickel cross-coupling reaction under very mild conditions at ambient temperature using the excitation of the dihydropyridine at 405 nanometers. And we could couple different aryl bromides with different type of radicals, benzyl radicals, or secondary carbon radicals, or primary radicals, if you stabilize them with an alpha oxygen. The very same photochemical strategy was then applied for the synthesis of ketones, starting from acyl chlorides. Then we tried to develop this photochemical cross-coupling process in an enantioselective fashion, since we like enantioselectivity indeed. So in particular, in this case, we needed to use this dihydropyridine, this racemic radical precursor that upon excitation could generate a stereogenic radical. And then we needed to use a chiral ligand, this simple box ligand, to bind the nickel, and this could forge the stereogenic center alpha to the ketone with good level of stereoselectivity. Also, using this particular radical precursor, we could install this indoor framework within the final product, again with high level of stereo control and good chemical yield. This is an example of photochemical asymmetric nickel cross-coupling process. Of course, we got an interest in trying to understand which type of radicals we could generate starting from this easily available starting material, this dihydropyridine, in this specific case using this carboxylic moiety. So this is a suitable handle for further derivatization, in particular through amide coupling, we could make these carbamoyl derivatives. This compound is yellow, can absorb blue light. Upon excitation, this leads to the formation of a carbamoyl radical that can be then trapped, for example, with nickel cross-coupling chemistry. This chemistry works well with aryl bromides, leading to the installation of these amide fragments and the formation then of the corresponding aromatic amides. Both primary and secondary amides can be simply generated. Of course, there are plenty of strategies for amide formation, but for example, we can also install these electron-poor amines that will be difficult to be installed because of the poor nucleophilicity when using, for example, classical condensation chemistry for amide coupling. But I would say that probably the future of this type of chemistry is the very mild reaction conditions, only light excitation and ambient temperature. And this allowed us also to transfer into the aryl bromide and to plug in a little bit more complex type of carbonyl radicals, being, for example, simple amino acids. And we could transfer different type of amino acidic residues without any erosion of the optical purity. This is because indeed of the very mild conditions of these amide synthesis strategies. You see, for example, this methionine or tryptophan can be, and also tyrosine, for example, can be translated into the final product with no problems of racemization. Because of the mild conditions, this type of methodology was also tested in collaboration with Bayer for the late stage functionalization of advanced aryl bromides, containing, for example, different type of polar functionalities of this type, or a lot of different stereogenic centers, or more importantly, probably for medicinal chemistry endeavors, we could also, this chemistry is also compatible, let's say, with a lot of heteroaromatic moieties. Again, because of the mild conditions, the chemistry works fine with no problem. So from this aspect, I think that this photochemical strategy for the synthesis of amides can be useful, maybe in particular, to install an amide fragment at the late stage in a complex molecules, let's say in complex settings. Okay, then we try to develop an AC radical, again, upon direct excitation of this dihydropyridine. In particular, in this case, we wanted to exploit the nucleophilic character of this AC radical. And to do so, we wanted to trap it with ground state electrophilic chiral aminium ion, a reactivity we discussed before. If successful, this 1,4 AC radical conjugated addition will lead to the formation of these 1,4 dicarbonyl compounds that are useful symptoms in synthetic chemistry. The main problem here was the very high reactivity and nucleophilicity of this AC radical that could attack the alpha-beta unsaturated aldehyde without the need of iminium ion activation. In other words, we needed to face a very strong background reaction that, of course, was racemic. We really tried everything, and my students did an incredible job. For a couple of years, they tried to optimize the reaction. The results have been okay, moderate. You see the enantioselectivity is not outstanding. Again, the main problem was the background racemic reaction. I want to highlight a couple of aspects that have been essential to achieve this enantioselectivity. That was to selectively use blue light irradiation, because in this way we could selectively excite this dihydropyridine. You see that this is really yellow. At this wavelength, the iminium ion generated upon condensation of this unsaturated aldehyde with the catalyst could not absorb. The maximum absorption is about 420, 430 nanometers. So here we are generating an AC radical upon direct excitation of this substrate, and then this AC radical is trapped by the ground state iminium ion. You see, the other aspect that was important for the success of this methodology was the use of this difluorinated catalyst that you may remember was designed purposely for excited iminium ion chemistry. But here we are using ground state iminium ion chemistry. So it seems that this catalyst that provided the best results in terms of enantioselectivity, also with respect to the non-fluorinated counterpart, let's say, it seems that this difluorinated catalyst can be very useful also for trapping radicals with ground state iminium ion chemistry. Anyway, I'll go back to this point in a couple of slides. Here, the scope of the chemistry, we can trap different types of acid radicals, aliphatic and aromatic. We can also functionalize at the beta position cinnamaldehyde derivatives. And now also aliphatic groups are tolerated. You may remember aliphatic groups are not compatible if you are exciting the iminium ion. But in this case, we are using ground state iminium ion chemistry. So what we learned from this study is that this difluorinated catalyst can be useful also for the activation of iminium ion in the ground state and trapping of a photochemically generated radical. So in principle, we wanted to identify or to try to explore the possibility that this can provide a general system for radical conjugate additions to unsaturated aldehydes with high enantioselectivity. And to do so, we needed to decouple the radical generation strategy from the radical trapping event. And this is why we use two different catalysts. This organic photoredox catalyst, the acridinium salt, that can be selectively excited at 460 nanometer, and it is needed for the oxidation of the radical precursor and generation of the radical. This difluorinated catalyst is responsible to activate the alpha-beta unsaturated aldehyde and to trap in the ground state the photochemically generated radical. And you see that also aliphatic unsaturated system can be functionalized with very high enantioselectivity. There are a different array of different radical precursors that can be used. Also, for example, we can use this cyclopropanol that upon oxidation leads to this primary radical. Generally, it is difficult to trap primary radicals with a high stereo control. This system seems suitable also for this type of targets. So the very last part, I would like to focus on another type of reaction that is not based on the excitation of organic molecules, but on the excitation of an organometallic intermediate. So it seems that also organometallic intermediates may acquire new properties, new reactivity upon excitation. And in particular, we focus on a classic organometallic intermediate in enantioselective catalysis, that is the iridium 3-pi allyl complex generated upon activation of an allylic alcohol, for example, with the iridium 1 catalyst. This iridium 3-pi allyl complex is a strong electrophile in the ground state that can be attacked by different nucleophiles, always with branch selectivity. And when we talk about asymmetric catalysis of the iridium 3-pi allyl complex, the best system is the one developed by Carrera, using an iridium 1 catalyst precatalyst together with this chiral ligand, this phosphoramidite olefin ligand, that leads to the formation of an iridium 3-pi allyl complex with always can trap a variety of different nucleophiles with outstanding enantioselectivity. So this is really one of the most effective strategies or systems, organometallic systems, for asymmetric catalysis using polar chemistry in the ground states. What we know about this iridium 3-pi allyl complex from Carrera? Well, we know that this is a strong electrophile in the ground state that is extremely effective in controlling the stereoselectivity. And also we know that it's bright yellow. I mean, this is not surprising, it's an organometallic intermediate, but we have seen during this talk another intermediate that in the ground state is really a strong electrophile, sorry, and also is colored, is bright yellow. That is the iminium ion. And we learned that if you shine light over the iminium ion, you turn a simple electrophilic compound into a strong oxidant that can start electron transfer chemistry, leading to enantioselective radical processes. So we wonder if it was possible to expand the reactivity of this iridium 3-pi allyl complex upon photoexcitation to make these a redox active oxidants. This idea finds support also in the fact that there are many iridium 3 complexes that upon excitation can do redox chemistry. So this was the idea, exciting this compound to make in the excited state an oxidant that can trigger radical processes. So we tried this model reaction. We made in situ the iridium 3-pi allyl complex by mixing the chiral ligand with the iridium 1 in the presence of the substrate, that is the allylic alcohol. Here, the main point was to irradiate the reaction mixture with a blue LED. Upon excitation, this compound should become an oxidant, able to take out an electron from this organic silane. Splitting of the silicon group leads to this carbon-centered radical. And this organometallic intermediate was then able to trap the radical with perfect site selectivity, branch selectivity, and with good level of stereo control. This chemistry, without light excitation, is not proceeding at all, no reaction at all. So it is again a photochemical process. Oops. Yep. So we tried also to get some information about the mechanism. We could isolate, it is already reported by Carrera, that it's possible to isolate the iridium 3-pi allyl complex. And then we studied the emission upon excitation of this organometallic intermediate. And we see that this emission can be quenched in the presence of this organic silane. This is a good backup, let's say, for the single electron oxidation of this compound leading to the formation of the radicals. We could also activate other type of radical precursors, such as these dihydropyridines, leading to this alpha amino radical. And again, we could trap them with this organometallic intermediate. Again, this is triggered by the light excitation of the organometallic complex. A little bit of the scope. There are different types of radical precursors that we can use, for example, having carbazoles or indoles or this hydroquinolone, or we can also, for example, functionalize efavirenz, that is a drug, and also type of compounds. As far as for the allylic alcohols that we can use, there are different type of substituents that are well tolerated. The limitation is that when we used aliphatic allylic alcohol, again, we shut down completely the photoexcitation of the iridium triiodide complex. Anyway, this study was quite interesting for us because we have found that we can switch completely, let's say, the reactivity of well-established ground state reactivity of this catalyst, that is a well-known organometallic catalyst used in many asymmetric catalytic processes, but with light, we can improve, let's say, or switch on new catalytic properties. In particular, we can make radicals, and then we can trigger an antiselective radical processes. To conclude, I want to thank all of my young co-workers, extremely passionate young scientists, and for me is a pleasure trying to help them understanding and using the excited state reactivity of organometallic and organocatalytic intermediates. This picture was taken already 18 months ago when the Melchiorre group turned 10 years at the ICIQ. It was still a time in which we could gather all together. I really hope that, and I'm sure that in a very short time, we will be able to gather together to discuss, to have fun, and to discuss about chemistry. That is the passion that all of us are sharing together. Again, I want to thank the organizing committee for inviting me to be part of this event. And of course, I'll be pleased to take any question you may have. Thank you very much.
Paolo, very inspiring and very pioneering lecture. Very exciting, real excited state chemistry. So I have several questions. Of course, probably the time won't permit to take too many, so I just start. For your first part, where you have added or used this bromo reagent or bromide reagent to generate the radical in the first part, the enamine catalysis.
Yes.
How about you take the CH bond and you do HAT catalysis? I'm pretty sure that you have already tried, you have thought about, but I guess there are some issues and things. Would you mind to share with us?
Yeah, I mean, we tried. I mean, you mean with the excitation of the enamines, right?
No, my question is if you take the CH bond to generate this radical rather than taking this alkyl bromide or this.
Yes. So in that case, let's say that we tried and we succeeded in some way with the medium ion excitation, because we could do the functionalization of toluene that in some way is a sort of hydrogen abstraction mechanism, is proton-coupled electron transfer. So we could really generate the benzene radical directly from the toluene. With the enamines, I think that we tried something not so extensively because it's more difficult to use the reducing ability, let's say, power of the enamines, because they are extremely unstable, short-lived, and so it's not that simple to develop reactions that does not go through EDA complex formation. So the point is that what you will need is to find a system in which upon electron transfer, you can generate an HAT precursor, right, that then can abstract an hydrogen. And this is something that it would be great, but so far we failed to do so. With the medium ion activation, we could do it.
Yeah, yeah. And my second question is, for your EDA complex, how stable in the excited state? Did you ever check that?
Okay, this is a very good question. No, I mean, we could not, at least we tried something with the enamines, but we were not able to see any emission from the EDA complex. So we could not study the photophysics of the EDA complex. I need also to say that we have done those studies when our knowledge as a group in photophysical investigation was a little bit, let's see, at the very beginning, and we didn't go back once we had a little bit more, let's say, skills with that. So we failed at the very beginning, but I think that, yeah, probably we should go back and try to see emission from the EDA complex. That will give a lot of useful information, I think.
Yeah, Adam, are you going to ask?
Yes, I have two questions, basically. Yeah, first of all, very nice talk. Thank you for being here today. A practical question, do you always also use flow reactors for your photochemical setups?
We have not done so. I think, I mean, no, I mean, for some reactions, for example, with the tryptophan functionalization that I briefly mentioned, in which we can do this selective radical functionalization of the indole nucleus in tryptophan dipeptides so far, let's say, we could implement that also in a sort of flow conditions. So, I mean, the combination with flow is clearly a great advancement or possibility for photochemistry. This is now well established, and there are many of you guys that are developing this type of approach. In my group, we are not looking in that direction very much, but I know that this can provide a lot of positive aspects, let's say, also in this type of chemistry. Yes, flow chemistry could improve, I mean, also our methodology. The point is that in our chemistry, we are a bit limited by the catalyst amount. It's difficult to go below 20%. That is quite high, even in organocatalysis, in which we are using it, let's say, not too expensive chiral catalyst. But for flow chemistry, probably then it would be quite expensive to go with this 20%, right, in the amount. And so this is why probably we didn't go much in that direction. But I would expect to be positive as in general.
Okay.
Adam, just a short interaction. So there is one very similar question from the.
Yeah, I see it.
So thank you for the inspiring talk. How fast are these reactions? Can we scale up?
And then the scale up, yes. This is a very pertinent question. That is, it goes in some way along the pathway that we were discussing with Adam. I mean, flow chemistry is absolutely the best way for the scale up, indeed, of photochemical transformations. So again, for our enantioselective processes, we never tried, because I think it would be too expensive and for the catalyst amount that we are using, in particular when we are using this difluorinated catalyst. I would expect a possibility to scale up the reaction easily, let's say, but this is more a guess based on some results that we have. The reactions are not always very fast, let's say 1 day reaction time, so they are not fast. We had other examples that I presented, for example, for the amide synthesis that was done in collaboration with the Bayer, and they scaled it up to gram scales. I think on the 2 or 3 gram scale reaction with immersion. I mean, it was not in flow, but I guess that in flow it could be even more productive, the process. So yes, I would say that for classical photochemical processes, flow chemistry is absolutely a way to go for improving scalability and the productivity, let's say. In our enantioselective methodologies, still we need to improve the catalytic performance of our catalyst in order to go down with catalyst amount. And for this reason, this was the main reason why we didn't try to scale it up.
Sorry, Adam, please.
Oh, that's full question completely answered. Also the second part, which I was supposed to ask. Thank you.
Okay.
So I can give maybe a word to Robert here.
Rob, please.
I also have a very simple and practical question, because I've seen that on some slides where you've shown the product scope, the yields were in some cases quite moderate, and I assumed that the molecules were very light or have low molecular weight. Is that a limitation, or is it more that the catalyst is fading, or the catalyst lifetime?
So the scope of those reactions, let's say, is not always very large. I would say, again, when we are developing the enantioselective transformations, there are many aspects that we need to consider. That means we need to merge the photophysical aspects of our intermediate with the fact that their formation also in a polar pathway, let's say, is not so effective. This is why it's difficult to go down with the reactivity. In some of those reactions, we destroy the intermediate. So, for example, in iminium ion chemistry, even if this difluorinated catalyst is more stable toward oxidation, still at the end of the reaction, we kill it completely, the catalyst. So this is one of the reasons why also the scope is not so extensive in some specific cases. Other strategies, I would say, are quite large in scope. Again, for the amide synthesis, this was mainly thanks to collaboration with companies that, of course, can provide much more complex fragments, and then it's easier for us to test the scope of the chemistry on those complex compounds. In that case, the scope was large. In some of the enantioselective processes, there are some limitations. And yes, that we are trying also to solve. There is always a reason behind. It's a mechanistic reason. Sometimes it's difficult to activate the substrates. Yeah.
Very final question. I mean, I have a question. I'll ask you later.
Okay.
Very final question from our colleague Thomas Werner from Leibniz Institute of Catalysis. So thanks for the great talk. If I understood right, the system in the first part proceeds via a radical chain reaction after initiation. Does the reaction proceed in the dark after initiation?
Okay, so this is a pertinent question. Many of the reactions that I showed in the initial part of the talk, mainly about enamine chemistry, they are chain propagation radical reactions. But if you switch off the light, the reaction stops for the simple reason that the lifetime, let's say, of the, determination is very quick. So you need always to feed in radicals to keep the chain working. It does not stop immediately, of course, but it does not go forever. So after few, let's say, minutes, you stop the reaction because you have a quite important termination in event. This is intrinsic to any radical chain propagation. So you need always to maintain the initiation event, that in our case is the photochemical excitation of the enamine. So the answer is no. If you switch off the light, the reaction stops.
Yeah. So Paolo, then I thank you very much for your great inspiring lecture, great chemistry, and
thank you very much.
All the discussions. So there is still one more question. If you get time, if you can answer to that question in the Q&A.
I will. Absolutely, I will in the question time. Thank you.
Paolo, thank you very much once again. Yes. Then now I hand over to Adam.
Okay. Hi. So let's come to our second talk after this homogeneous catalysis talk, and let's now become a bit heterogeneous. And it's my great pleasure to introduce our next guest, Professor Bradley Schmelker from the University of California at Santa Barbara. Professor Schmelker graduated with a Bachelor of Science in Chemical Engineering from Arizona State University in '82, and then he went to industry for 2 years to work as a startup engineer. But he returned quickly to academia after 2 years in '84 when he enrolled at the UC Berkeley with Alex Pines as supervisor for PhD studies, which he finished in 1990. He was then shortly after awarded a NSF postdoc fellowship, and he stayed at UC Berkeley to work further on NMR spectroscopy until '91. And then he received another fellowship, an NSF NATO fellowship, and he left the US to Germany, and in particular to the Max Planck Institute for Polymer Research in Mainz, where he stayed until '92. And looking at his outstanding research, it was actually not a big surprise that many universities wanted to hire him as assistant professor. So then in '92, Brad returned actually to the US, and he joined the Department of Chemical Engineering at UC Santa Barbara, where he established his own research group. And then he was quickly promoted in '95 to associate professor and in '99 to full professor. Brad also received numerous awards and honors, and I will only mention a few because the list is so long. So, for instance, he has been elected to the Royal Swedish Academy of Engineering in 2017 and the Royal Swedish Academy of Sciences in 2015. He's also the co-director of the Institute of Collaborative Biotechnologies within the UCSB MIT Caltech network, and he has been guest professor in Israel, Spain, Sweden, and France. And the Schmelker group works on the correlation of macroscopic material properties and function with molecular structure and dynamics, and in particular in heterogeneous systems. Today, Brad is here with us already actually since 7 a.m. morning, Santa Barbara time. And Brad, we are all looking forward to your talk, which is entitled New Mesoporous Nitrogen-Carbon Materials for Electrochemical Energy Conversion Applications, Understanding and Design at the Atomic Level. With this, the show is yours, Brad. I give the word to you, and we are looking forward.
Okay, let's see. There we go. You can see my screen, I hope. Let me. How's that? Everyone can see that?
Yeah, it's working. Perfect.
Well, thank you, Adam and Robert and Shubik. This is a great pleasure, and with the as Paolo mentioned, despite the restrictions on travel, this presents really an opportunity to actually read much more broadly than we would if we were just in person for a seminar in each of our own respective home universities or institutions. So this is terrific, not limited by really location or time zone. So it's early morning here still, and I really appreciate you being tolerant of my being able to participate a little bit later in the day in Europe. So as Adam mentioned, I have broad interest in the areas that impact on the main topic of this particular seminar series in sustainability. From my time in industry, which was in fossil energy, that I've always been interested in aspects of materials and processes for energy conversion and using those precious resources efficiently. And that would seemingly be certainly far from burning them. And along the line, we've studied different aspects of these types of materials for such processes and brought to the aspects of synthesis in-house with detailed characterization, which provides some opportunities not only to improve the materials for which we are working, but also to understand them so that we see correlations and opportunities to connect different strategies for improvement across very different types of material space. I'm going to tell you about today these mesoporous carbon materials, which involve extensive collaborations with not only within the US, but also in Europe. I draw your attention to, well, mainly the 4 outstanding PhD students who've worked on this over the time. Dong-Hoon Kim on the right started this. He's now on the faculty in South Korea. Zach Berkson is a postdoc at ETH with Christoph Koppere, who spoke to us a few weeks ago. Niels Zasblad is with Intel, and Shauna Beckwar is finishing her PhD this coming summer. I'm going to speak about this, especially for these carbon materials with earth-abundant components for oxygen reduction applications for fuel cells, also having applications in batteries, and we think water purification and supercapacitors. But we're going to focus on these oxygen reduction for now. It involves some nice synthetic chemistry that we were fortunate to learn from Nina Feschler and Marcos Antonetti's group. We're working especially with the group of Philippe Sauté and Xiongfang Duan at UCLA in a Department of Energy funded fellowship, which supports this work currently. I know Adam from my time in Stockholm on sabbatical and was conducting some electron microscopy works with Tom Thersleff there in his department. And we've been working with Chalmers University, Anders Palmquist and his group, Teledyne, to promote some commercialization of some of these. So I don't know that I need to motivate it, but because we're all convinced on that in this seminar series, but I want to tell you what the crucial, I'd say, need is for us to solve climate change, okay? We all know we burn too much CO2 and it's escaping, but here's the conundrum. We can solve that if we have the discipline, but I think our societies probably, with few exceptions, don't have the discipline to actually restrain that carbon dioxide footprint because we don't have alternatives that are sufficiently attractive right now. We're getting there, but that's the problem. And the problem is, I show here, is manifested by this nice article from a few years ago that shows what happened during England during the Industrial Revolution. And this is a scale of annual energy consumption per person in the UK before the Industrial Revolution, and you see as the Industrial Revolution takes off. And this big orange bar is coal. The rest of it is human power or forest or firewood and animals, but this is the big one. This represents a 10-time increase in energy consumed during the Industrial Revolution, which brought forth all of by extrapolation, the benefits we have now. At that, or about that same time, this is from Sweden, different country, I realize, but this is now looking beyond that, 1800 to 2000, and the value of energy per GDP, with respect to per GDP of Sweden, and it's going down by a factor of 10. So you have an increase in consumption of energy coinciding with the betterment of society, coinciding with a decrease in the price of energy. That's kind of counterintuitive. You'd expect as the energy consumed goes up, perhaps the demand goes up and the price would go up. The opposite was happening. And that's because these fossil energy sources are inexpensive and they have high energy density. They are directly responsible for our sort of prosperity globally, elimination, or for at least great reduction in world hunger because of greater food security, because of inexpensive fertilizers, thanks to another important heterogeneous catalysis application, the Haber-Bosch reaction. 300% increase in crop production, just in only 1970. So these cheap energy sources are plentiful and will continue to be plentiful throughout our lifetimes. Coal is around for even longer than that. The problem is that these cheap energy sources are basically too cheap in terms of the costs that they are manifesting that are not properly accounted for in the market value that we attribute to them. And these environmental costs are becoming increasingly large, and one can argue they're going to be dominant here very soon. And this is just a reflection of the tragedy of the commons. There's no really easy way to police or enforce the reduction of carbon dioxide. So cheap, abundant prosperity, that's the problem that our governments face. And with few exceptions, I just don't know that that's going to be something we can put that genie back in the bottle. So I think, and I'm not alone in this, but really the only way we're going to get out of this is if science and researchers can develop new and inexpensive, efficient energy sources and materials and processes in order to give our societies, better options so that we can retain the energy consumption without producing CO2 and doing so in an inexpensive way. So that's the challenge. So in doing this, we have to many aspects to this problem, and it's this energy environmental nexus that my group works at. And I worked in fossil energy back in the day, and so I understand that, and I think it's these fossil sources of resources are probably very, very beneficially used and have been for fuels and chemical manufacturing, but under conditions where their value is perhaps used and not just burned as a source of energy. We worked a lot in the center one here in zeolite catalysis, and that's responsible for a lot of the refining, and that has led to the prosperity that I mentioned. We're also working in similar types of materials for zeolites and heterogeneous catalysis for automotive pollution mitigation, for looking at denox catalysts that would involve using non-precious metals to remove nitric oxide from diesels and automobile exhaust. We've worked in the areas of cement and structural materials. These are responsible for something like 8% of anthropomorphic greenhouse gas emissions, just the structural material. One can argue that cement is the most important synthetic structural material in human history. It was discovered by the Romans and it's still being used. But there are ways to do this, perhaps using examples from biology, biomineralization, these calcium carbonates and siliceous diatoms, from which under genetic control can develop these kind of architectures. And so we're working to look at developing low CO2 type cements. Interestingly, aluminosilicate cements are basically similar chemistry to the way you create and synthesize aluminosilicate zeolites. And so the atomic level chemistry in the process and crystallization and control that we are using to study the two really complement each other quite well. I'm going to talk more on this on the left-hand panel, because one can argue that these right-hand side of this slide deals with the aspects of what inexpensive fossil energy or materials that have produced a lot of CO2. The ones on the left represent more of a solution to that. And so with my colleague Ramses Chaudhry at UCSB and Shuji Nakamura, he's the inventor of one of the inventors of the gallium nitride blue laser, we're using these kinds of things to look at rare earth doped phosphors to upconvert light downconvert light from indium gallium phosphide blue lasers into white light for solid state lighting applications, organic solar cells, solar electric energy conversion, and I'm going to talk about this fuel cells and batteries. Now, what you see here are all interesting and very current states of the art in certain materials across all these applications. And what they share, though, is aspects of non-stoichiometric heterogeneous solids, which have properties defined principally by the non-stoichiometric component, whether it's a dilute amount of rare earth dopant like cerium in a otherwise ceramic YAG matrix, a nitrogen doped carbon or a aluminum or boron doped zeolite, these are all the central active species in an otherwise crystalline material, but because they're non-stoichiometric, they're not easy to study. So these solids are complicated. There are big challenges associated with trying to understand them and improve them or even develop them, because they're synthesized under multi-component, non-equilibrium, and generally transient conditions and properties. They have mixtures of order and disorder on different length scales. So you see what I show here. Most of these in these cartoons look crystalline, but in fact, it's the non-stoichiometric distribution of these functional A species, like these aluminum heteroatoms in the zeolite that I show here, or the non-stoichiometric distributions of nitrogen in these carbon materials, which we're going to pay close attention to. These are the things that basically are not easy to understand or characterize, because their distributions and local structural environments are crucial to the properties. Their distributions, and these are these key functional species, and they're often dilute and non-stoichiometric, as I mentioned. They have interactions and reactions at surfaces. As a chemical engineer and for catalytic applications, these are all at surfaces. Surfaces are inherently disordered in a way. And they have often mass and energy transport limitations, which govern properties on top of the intrinsic kinetics. So all of these different aspects that I've just mentioned here have aspects of local or long-range order, which are difficult to disentangle. And so our hypothesis, and throughout all these different types of problems, is that we can correlate. We should be able to correlate, where we seek to correlate, the atomic level compositions, structures, and interactions of atoms and molecules in these materials with the synthesis, characterization, and macroscopic material properties, and feedback to improve them. And by doing so, we see analogies between the various ones, which gives us a nice creative cross-pollination of ideas and results that we can take across these different types of materials. So the example I want to talk about here is one of these current challenges. I'm going to speak specifically about hydrogen fuel cells, because there's a lot of work now being done, especially in the United States anyway, about decarbonizing natural gas, for example, as a source of a fuel cell. Now that is not that's not as sustainable as using something from maybe a biological or a solar source, but I expect in the future we will have sources of hydrogen, which will then allow these hydrogen fuel cells perhaps to be used more ubiquitously. Now, they have they're based on the fact that you can take hydrogen, and it comes in on the left here, and it absorbs on a platinum, typically on supported graphitic activated carbon anode. It removes an electron as from the absorption, passes through a circuit to do work or whatever it does. The hydrogen ion that it comes across from the electrolyte absorbs on another platinum on cathode electrocatalyst, which now reacts with oxygen to form water. And all that is the basis of a hydrogen fuel cell. The problem is, in this case, the rate limiting step of many of these types of devices is this cathode reaction of the oxygen reduction. So this reaction is slow. It's often the rate limiting step, as on the left. They use platinum on carbon. And in fact, so you can accommodate that by somehow increasing the amount of platinum. And so what's used conventionally is something about close to 20% platinum is used dispersed on a conductive activated carbon support. So this is about 4,000 meters squared per gram. And so this 28% platinum is the problem, right? Because this accounts for, on the right, the projected fuel cell costs from the Department of Energy in the US government, is that the platinum costs about 41% of the overall cost of the device. And that's because this 28% platinum is just really extreme, and that's why you don't see these things except in very specific and very high, very niche applications. The technology exists, but it's this 28% platinum is the problem. It's also supported on this activated carbon, and that's nice because at least it comes from a sustainable, inexpensive sources. I show here where an example of from pyrolyzed coconut shells, or other sources are walnut husks, and they tend to be biological sources because they're inexpensive. They pyrolyze, that is, they convert them from these organic sources into these graphitic type carbons, the activated carbon support at high temperature in the absence of oxygen. But you end up with a pore size distribution, something like this. So most of the pores are in this area peaked around 0.8 of a nanometer. And the problem with this is that even though you have 4,000 meters squared per gram surface area, the pore sizes are such that you have severe mass transport limitations to get to that high loading of platinum. And also in the case of some of these water, with water, often, well, if you have ions present, hydration of ions can't enter them easily because there's big mass transport limitations just based on the steric exclusion because of the small sub-nanopore sizes. So we thought there was an opportunity here, at least in a couple of different aspects, to actually improve on this aspect of the oxygen reduction catalyst. And so what I show here on the right, on the bottom, are what I consider desirable property objectives. Earth abundant species, that is something other than platinum, high electrical conductivity, carbon is fine for that. High surface area, well, the carbon's fine for that too. Facile diffusion of reactants and products, that's not so good for the activated carbon because of this small sub-nanometer pore size, and high density of accessible surface active sites, okay? So the real hard one, I think, is getting the active sites that you want, which would catalyze these reactions. So we're not the only ones, and many others, and in fact, Adam has worked in this recently too. He had a very nice paper that I cite here on the upper left hand, where one can take carbon supports, activated carbon or others that one can make, and pyrolyze it to create a porous carbon, of different ways of doing that. But carbon itself is not active for this, and so one needs to introduce the active site. And nitrogen is this heteroatom incorporated into the carbon is a good a candidate for these types of oxygen reduction reactions, and has been demonstrated by others. So you have to introduce the nitrogen somehow. So that's where these different methods kind of differ. So among others, they use the cyanofunctionalized groups, the nitric acid, ammonia to introduce it. And then one aspect of that is it's usually going to the surface where it is desirable. Others here where you take carbon nanotubes, these or these porphyrinic type materials, they have these nitrogens in these macrocycles. These also have been observed to catalyze this oxygen reduction. These are rather expensive to make. Or another examples are these cross-linking precursors where you have a lot of nitrogen. So you actually start with a nitrogenous precursor, and then like there's imidazolium or these other ones. And Marco Sanguinetti has done a lot of work in this area, and that's where we kind of started interacting with him, is that by having a lot of nitrogen in it in the first place, you hope that some of it will stick and stay as you basically pyrolyze and drive off the volatile species. That's not always the case, and often generally doesn't occur. We've worked on this too, starting a few years ago with Dong-Hoon Kim, where we're using formaldehyde and this melamine. This has basically a lot of nitrogen in it, and that is also one which actually had some nice oxygen reduction properties. But the trade-off is generally this: as you increase the nitrogen content, looking on the left, you have this increasing nitrogen content. You end up getting from the more nitrogen you get in, the less conducting it becomes. Right? The conductivity is kind of inverse to that, and you can kind of see that with the carbon nitrides. You can get 50 weight% nitrogen in, but they have low conductivity. Whereas the nitrogen-doped carbons, typically in this 2 to 4 weight%, so you almost never get more than that, have higher conductivities, but with lower nitrogen contents. And so typically, these things are prepared by pyrolysis, which in order to drive off the oxygen as much as you can, and the hydrogen or other volatiles, such that you graphitize the carbon that's left behind. So it tends to be a very difficult to control reaction, greater than 800 degrees Celsius, and that high temperatures tend to volatilize, especially the nitrogen species. So it turns out the nitrogen species are selectively volatilized over the carbon. And so the nitrogen, and so what ends up happening is we end up on almost all these different ones, including our own up here on the lower right, on the central right, the surface nitrogen contents are rarely, if ever, over 4 weight%. And so even though you start with something like melamine or these other high nitrogen ones in the center, you get very little nitrogen in the end. And most of these expensive precursor components is just volatilized into the atmosphere. So that's been the state of the art, basically, until what I think is close to now. So the way we've approached it is working with Nina Feshler, and Marcos a few years ago. Nina visited our group and we discussed with her about this possibility of at least expanding the pore size by incorporating this into a template of mesoporous silica. So the chemistry and the organic chemistry is simple. It basically uses urea, carbon-13 with 2 nitrogen groups. This more interesting compound, this precursor, cyclohexane hexone, and this has got this like cyclohexane ring, but with these the double bond oxygens coming off each of the vertices. And so these aren't obviously good candidates because the urea melts at 133 degrees Celsius. The cyclohexane hexone is not a very stable molecule and it decomposes at only 99 Celsius. But by mixing them together, they have this very fortunate, very fortuitous thermodynamic property that when mixed together, they form a eutectic mixture. That is to say, the eutectic mixture in a thermodynamic sense is a mixture of the species that is low melting. And so the melting temperature of this stoichiometric mixture of 3 urea molecules to 1 cyclohexane hexone, while the individual components would decompose or melt or not melt soon enough, they have a melting temperature of only 68 degrees Celsius. So by processing them between 68 and 99 degrees Celsius, we form a nice homogeneous low viscosity melt of the mixture into which we can imbibe it into these a porous template, and I'll show in a moment. So here after this melt, we polymerize it, it cross-links, locks in essentially the nitrogen, and then the pyrolysis reduces it to this graphitic into which we now have nitrogen contents that are quite high. So we do so by, and coming from Santa Barbara, where we developed a number of years ago, the use of block copolymers to form mesoporous silica. We use that mesoporous silica to incorporate this low viscosity melt, as I show here, into those pores. We then pyrolyze it and then etch it away in sodium hydroxide, creating an inverse replica. So as I show here, the bottom left is a transmission electron micrograph showing the dark honeycomb-like structure of a nice SBA 15 hexagonal mesoporous silica with no carbon in it and not even reactive, has pore sizes of approximately 8 nanometers, or not pore sizes, but pore size of about 4 nanometers, separation from center to center of about 8 nanometers. And when we convert and incorporate the various precursors, or nitrogen with or without, we basically get the reverse. Sorry, so we end up having now the posts now become carbonized. They're graphitic-like, and the separation, the spaces that was the silica that is now open space, and that's the region over which now the molecules can diffuse in. So this has the benefit of reducing the mass transport limitation because the pore dimensions are now much larger and can promote better diffusion of reactants and products from within the pore structure. And this nice electron micrograph you see here shows the posts with the separating light areas between them. So there's that, and then with Marcus, there's and Nina, they had used another type of porogen. In this case, it was a mixture of sodium chloride and zinc chloride salt. Turns out it's the salt and the composition of that salt, I'll tell you at the end, is important. It forms a eutectic melt itself, and it leads to a much less ordered mesoporous material that I show here in the schematic diagram, into which then you can incorporate this low viscosity melt, pyrolyze it, dissolve the salts away in water, and you're left with this replica structure again with pore sizes that are about the same. So this is the chemistry that is really useful. And the reason why is this, because these low viscosity melts of these eutectic mixtures provide some very helpful properties that sort of give rise to material properties that are really quite promising. And what I show here is why we got interested in this. Okay, so it turns out these mesoporous carbons with nitrogen in them, without anything else, just nitrogen carbon properties, have very favorable oxygen reduction activities and properties. Now, but they're different, and that's the part that becomes now the plot becomes even more interesting. So looking at on the left, we form these mesoporous silica template, and they have surface areas of about 1,100 meters squared per gram. So less than the activated carbon, but bigger pores for easier mass transport. Again, we're not the first ones that use those in that way. Professor Yang Ryu and Keist in Korea, and Dongyuan Zhao and Fudan University, who people, good friends of ours who I know very well, we'd followed a lot of their creative initiatives in this area with respect to MCM type materials and others. But with carbons, and this is now we were looking with nitrogen. That the nitrogen part again is the crucial one. With the zinc chloride salts, we get somewhat higher surface areas, 1,800 meters squared per gram, about the same pore sizes. And if we look down at the center, we use from XPS, we see that from, which tells us about the surface nitrogen composition, we see that the silica templated and here in the purple has approximately 16% nitrogen, the salt templated about 11%, and these are substantially higher than what I had mentioned previously were the typical nitrogen loading. So we've increased by 3 to 4 times the amount of surface nitrogen compared to what has typically been possible with the more widespread efforts to introduce nitrogen into these. So this synthesis that I just described introduces a lot more nitrogen into this. And I don't think we don't even really call them doping anymore, because these are sufficiently high that they're really nitrogen containing materials rather than nitrogen doped. They're really quite a lot of nitrogen in them. What's fascinating though is how different these two materials behave when it comes to the electrochemical properties. And that's what we're going to spend time talking about, because here I compare them to the 28% platinum on activated carbon, which is in the black. The onset potential here is for platinum, on this platinum is about 0.98. For that of the salt template one is about 0.93. So not quite as high an onset potential, which is a little bit less suitable, but has a limiting current down here that of about minus 3.8 milliamps per centimeter squared, which is practically the same as the 28% activated carbon. So this salt templated material has really interesting properties with no platinum whatsoever, gets very close to the properties that you would desire for these hydrogen fuel cells. So this looks like it's got some potential commercial opportunity. By comparison, the silica one, which has even higher amount of nitrogen in it, has basically much worse properties. And so that is somehow sort of made us curious as to what's different about those, because the organic chemistry is the same. We're not doing, all the conditions of these preparations are the same except for the templates. And we'll talk about what we think that is. First of all, we have to know why that is and what those differences might be. And so if we look at another desirable property, we have the stability of these materials. After running this for several hours, the salt templated maintains its within up to about 90% of its original performance properties, compared to 78% for the 28% activated carbon and 51% for the silica. So the salt templated one has not only nice activity, but also superior stability for long-term performance, at least for moderate-term performance over many cycles. Okay, so why? Well, these reduction activity depends on factors other than surface nitrogen contents, that's for sure, because these 11% weight and 16% are actually the opposite of what you might expect. And so all nitrogen sites in these materials apparently may not be equivalent. And therefore, if they're not equivalent, they may have different activities for these electrochemical properties. Or by the way, if you're not interested in fuel cells, water treatment, supercapacitor properties, or battery type things, these are all correlated with in a different way with these nitrogen sites. And the nature of those sites are going to be probably important to each of these different applications and reactions. The question is, why? What types of sites are important? And I'm going to use the example of the oxygen reduction to sort of to basically show you what we can learn about them. So first of all, we're going to look at what's conventionally known and what using conventional methods. So the pore sizes are about the same, 3 to 4 nanometers. That's not expected to be very different and not expected to count for the properties. The nitrogen contents are a bit different, but in fact, they're the opposite to what you might expect. If we look at X-ray diffraction on the left, we have broad reflections at 26 degrees, and these other ones at around 41 and 44 degrees. And these are consistent with the graphitic long-range periodic order of graphitic sheets from these materials that we pyrolyze and they're essentially the same for the two of them. They're very little different. If anything, the salt one is a little bit more disordered long range. Raman spectroscopy is sensitive to the bond vibrations of these carbonaceous domains, and you have these D bands and these G bands, which are associated with edges or highly graphitic structures, and they're about the same for both of them. So that's not different enough to count for these big electrochemical property differences. So there's minor differences in the extent of graphitic ordering, but not enough to account for the differences. The differences, we do see some minor differences in the XPS. From the nitrogen profiles, we see the binding energies. And so if compared to a non-porous version of this and a silica templated, there are some differences, but basically the problem with XPS is you can see, we get poor resolution of the different signals, so which we can get some inferences, but can't say anything very confident about the different species, other than it looks like there's maybe pyridinic, pyrrolic, graphitic, nitric oxides. Hard to say very much about this in a unique way from what the XPS can tell us. NMR, in principle, can tell us more. And Adam's recent paper talks about nitrogen carbon NMR, and that's something that we are using too. I'll tell you the challenges of this. In the case of these particular materials, they're highly conductive, and that electrical conductivity is actually not good for NMR. It tends to expel lines of magnetic flux, and so we have to use techniques to dilute them and get skin depth issues and powder them such that this conductivity can be somehow managed. It also contributes to very broad signals, and as well as due to the broad distributions of local nitrogen and carbon environments. And so what I show here is we've taken the trouble to enrich with nitrogen-15 and carbon-13 the urea. So we do that because carbon-13 at natural abundance is only 1.1%. Most of it is carbon-12, and so a little bit is carbon-14 for radioactive dating, but there's 1.1% that behaves like has a unpaired neutron, and therefore has this aspect of magnetic resonance properties. Nitrogen-14 is the one that is the predominant isotope of nitrogen, but nitrogen-15 does exist in nature, but at very low natural abundance, 0.4%. So typically one has to enrich that, or one can use dynamic nuclear polarization, which we were not able to use here because of the electrically conductive properties of these materials, which basically absorb microwaves. Or some of those, so you might be familiar with some of the revolution behind dynamic nuclear polarization that's meaning to the spectroscopy facility community. These are not amenable to that because of the conductive nature of them. So we go through the effort to isotopically label the urea and incorporate therefore, and then can use this 98% N15 enriched 25% enriched carbon-13 to look at these different signals. And what you see for the carbon is, well, a broad blob. You'd say it's mostly in this aromatic region out here. Can't say anything better than the XPS about really what's happening here because the line is basically featureless. With the nitrogen-15, we see two distinct broad blobs. But again, based on this, and this has been the state of the art for these materials, and why not much more has been done. But what we're able to do now is we have this with the enrichment, with the ability to go down and lower the temperature, and with the higher nitrogen content, we're able now to use two-dimensional methods in order to do much more from this. So what we're going to do is we're going to take the analogy from what has been done for a long time for biomolecules in solution. Okay, now biomolecules in solution have an aspect of where they have no long-range order. So you don't do X-ray diffraction for protein in solution. What you do is, and what is done, and this is Paolo is from Barcelona, and so I spent a year with Miquel Pons and Ernest Gerald in Barcelona at the Parc Scientifique learning about protein NMR. And Miquel's group here a few years ago published this nice structure of this protein where they enriched the protein in nitrogen-15 and carbon-13, and then use the aspect of dipole-dipole couplings between these two nuclei in order to get information on their proximity. So basically, think of each of these atomic nuclei of nitrogen and carbon-13 and nitrogen-15 as little magnets. And they have these lines of magnetic flux that I show up here on the upper left-hand corner. In a magnetic field, these things, they're going to be, if they're far apart, they behave like little bar magnets, individual, and they have the resonances that you would see. But if you bring them close together, and close together means very close together, because the dipole-dipole couplings between these two nuclei scale as the reciprocal cube of the separation distance. So that, and so this actually de facto means within about 1 nanometer of each other, they influence each other. Just like if you bring 2 bar magnets nearby, they start influencing each other also. So these couplings reflect proximities that one can use to correlate the isotropic chemical shift of a nitrogen-15 atom in its local environment with that of a carbon-13 atom in its local environment, and selectively detect pairs of them. And so the way that works is you excite the carbon-13 signals with a nuclei with a 90-degree pulse, but not the nitrogen. The carbon-13 atoms that are near nuclei that are near the nitrogen-15 transfer their polarization on the lower left here to those nitrogen to which they are dipole coupled. We then increment the experiment over a series of measurement times such that we measure the nitrogen-15 frequency in its local environment, transfer the magnetization back to carbon, and then detect the carbon. We do a Fourier transform of the carbon signal and a Fourier transform of the nitrogen signals. And what that allows us to do is we get this 2-dimensional frequency map of a carbon-13 frequency on the bottom and a nitrogen-15 frequency along the vertical axis. And what you see is these topographic maps of signals, which is intensity, that correlates, for example, this one up in the upper left-hand corner, the signal at at 112 parts per million, hertz per megahertz of nitrogen, with a signal of carbon at about 70 parts per million or hertz per megahertz. And that Mikel and his coworkers were able to assign to specific amino acid moieties from which then they could do this elaborate structure solution strategy in order to determine the structure of this molecule, even if without long range order. So this dipolar mediated 2-dimensional methods are extremely powerful, okay? And so we apply that to these systems. Now, our partially ordered systems are solids. They're not highly ordered. And so our spectrum is going to look very different to what you just see there. In fact, it looks like this. And by comparison, we see the carbon-13 signals across the top is, again, this big, broad blob. Nitrogen-15 on the axis, big, broad blob. So the 1-dimensional spectra that you would normally use, or has been used principally in the past, are largely useless for this because the resolution is too poor. That's been, I would say, the obstacle to understanding these materials more. But what using a similar type of experiment to what the biochemists did in Barcelona, we're able nevertheless to see areas of distinct distributions to which we can assign different moieties that are going to be dependent on the templating species we see. So for this mesoporous salt templated one, what we see is these blue regions, which are nitrogen here around around 160 ppm or so, correlated here, this in a distribution that is associated with graphitic, nitrogen and graphitic environments. And we think those are principally those like in the centers of these sheets where it's a flat sheet and you've got a nitrogen in the center of it. We also see ones where we have these isolated pyridinic groups, these yellowish ones. And the yellowish ones are these others which actually are here at the bottom where you see that there is where it's kind of not bonded to hydrogen and it's basically there on the surface. And this will be an important one. We also see ones where we have the high nitrogen content. There's some paired nearby structures that influence each other, these pyrazinic ones. And then there's some green ones which have some nearby of the graphitic and these pyrazinic ones which are near each other. Now, that resolution still presents us difficulties with understanding what types of structures we've got. So with this, we've been really fortunate to work with a very clever graduate student, Ziyang Wei, in Philip Sauté's group at UCLA, and Philippe and Ziyang and I, we're closely with Sean Beckwar and I, in order to model these by using density functional theory to establish what the local environments are in the electron density and the shielding of the nuclei of carbon and nitrogen for a variety of different inventory of model structures. So I show some of those for that Ziyang has tried. There's these pyrazinic ones up on the left. There's these other ones I show that the hydrogen, there's these small little atoms up here, carbons in the gray. The first nearest neighbor carbon is in black, a graphitic nitrogen here. For example, this is one I show in the graphitic, there's a graphitic nitrogen in the center here. And what they can calculate for these structures, they can model basically it's a graphenic sheet where they model the different electronic environments, get a chemical shielding from it, and the chemical shielding for this carbon next to that nitrogen would be about 121 parts per million. So I show down here, and we can put it on a sort of a hypothetical spectrum. The nitrogen 15 chemical shift is can be calculated for its environment in this graphitic sheets, and it would be about 128 or so, and put it there. And then we can do this for all these different types of structures. There can be depends on local geometry, depends on another heteroatom proximity, first or second nearest neighbor effects out to 2 or 3 bond difference, whether there's an adsorbate atom nearby. And what Ziyang is able to do, you can now take this nitrogen 15, carbon 13 type spectrum and put a point where each of these structures would have its calculated shielding of this. So what you see up here are these regions corresponding to these different types of graphitic nitrogen with different local geometries, different heteroatom proximities, and different next nearest neighbors. And there's clusters of them: pyridinic, isolated pyridinic, pyrazinic, isolated pyridinic, and graphitic. Now, if we overlay this lower one right with our spectrum, this is what we get. So we're using a similar type of experiment to what is used by the protein community, and now overlaying those DFT calculations with the two-dimensional NMR spectrum that I just showed. And what you see is with something with, we think, a gratifying resolution. We see the graphitic nitrogen carbon signals are right on top of this main peak. We see some evidence of some of these others that are off, that don't fall in that intensity. And that's okay, because we just realize, we can, I think with confidence, say we do not detect those species to a significant extent in the material that we have. But these are consistent with us having not only the distribution of species, but it's what accounts for both the location as well as some of the distribution of that signal. That also goes for the pyridinic and the pyrazinic ones, such that we really, I think, have now much higher confidence that we can now identify what the structural features are of these graphitic nitrogen-containing carbons are, which are now going to account for, I think, the properties that we showed in the electrochemical device. So when we compare this salt templated material, which had the good properties, with the silica templated, what you see here, you see that the silica templated has the same overall types of features. We have graphitic, we have these pyrazinic and the pyridinic, but the distribution is not the same. It's not the same. And that is the essential essence of having types of different nitrogen-containing heteroatoms, but for catalytic activity, you need ones that are just right, that need to be the right ones. And so what you can see from this is that, and this is the density functional theory is impressed in Journal of Physical Chemistry. This particular work I'm talking about now is submitted and under review. What we notice is that there's a pretty big difference in this region of this 2D spectra. And that suggests that these are the species that are the ones that are central to the oxygen reduction reactivity property differences that we detect. We have a lot of graphitic ones. We have the pyrazinics. It could be the pyrazinics and these paired pyrazinics too. But this is the ones that look like are probably the most likely ones. And if we then take the benefit of the two-dimensional positions and resolutions of these now much more resolved frequency maps that enable us to make these assignments, which you couldn't make otherwise, really, with respect to this without the two-dimensional characterization analysis. We now can use that with quantitative measurements with directly excited nitrogen, which then reflects the relative populations of these different nitrogen species. And what we can see is that these different nitrogen species for the salt templated and the silica templated, again, have similar species, but there's population differences, especially these isolated pyridinic ones, which are approximately 40% by best we can estimate, of the quantities of the nitrogen in the salt templated ones versus that of the silica templated ones. And we think this is the most likely aspects for why these materials are behaving the way they are. So the question would be then, okay, if that's the case, are they surface sites, right? Because bulk NMR is a bulk technique. So we can see different distributions, but NMR is by itself in these methods, it just tells you that they're nitrogen and they're carbon. It doesn't tell us whether they're surface sites. For that, we can use a related NMR measurement. and that's looking at using water, which is useful as a product of the oxygen of the reduction reaction. We can absorb water, and water will, after following pyrolysis, we have a dry, very dry material. We absorb water on it, and the water absorbs at surface sites. So we hypothesize that you could, if you take the absorption of water and then transfer by just simple cross-polarization through these same dipole couplings to nitrogen, you don't excite the nitrogen directly, you only excite the nitrogens that are near the protons, hydrogen ions, hydrogen molecules associated with water, and then detect the nitrogen. You detect only those nitrogens which are accessible to surface moisture, surface water. And so as I show here, we have this nitrogenous carbon, we have surface absorbed water in the pores. The water, by chemically absorbing, is within this nanometer distance such that dipole couplings permit the polarization transfer to occur, and we use that as a filter to look at essentially only the nitrogens containing hydrogens. And when we do that, we see this nice cross-polarization, magic angle splitting NMR spectrum in the solid state material, and the dried material is shown in red. The dried one here has a big signal from pyrrolic nitrogen. Well, that's not surprising, even though the pyrrolic nitrogen here in the purple up in the left is barely visible and accounts only for 2 to 3% of the overall signal. All of them have hydrogens attached to it, so its signal just is really high, and it's basically the same for both of them. When we absorb with before and after absorption of water, but after the absorption of water, what we see is that a big increase in the signal from the pyridinic and the paired pyrazinic, and these correspond to those, and not from the graphitic. And so these are the sort of the proof, if you will, that these species here, these pyridinic ones, which don't have hydrogen on them except when the presence of absorbed water to any extent, are on the surface and accessible. So we're confident now that we've got the crucial sites identified, and that this is the thing that now we know we can go back into our syntheses and sort of ask, okay, what is it about it that led to these sites being favorable for the salt template and not for the other one? So I'm approaching the end of my talk, but I want to address that part, because one thing I like about this this kind of story is that we were motivated by the properties. We had some materials and characterization. I'd say unique combination of properties that allow us to do this, but it gives us an opportunity to really understand perhaps what's going on. So when I mentioned that the cyclohexane, hexone, and the urea had a low temperature melting eutectic that was advantageous, turns out that's also the case for the salt template. So if we look at this, this is a phase diagram for a zinc chloride, sodium chloride. And if you have it as a function of temperature here, and you have the relative mole fraction of sodium chloride. So if I look at this, we took samples. This was Niels Zusplaat before he finished his PhD. We took samples at 10, 30, 50, 70, and 90%. And that's what these histograms are on the left are. And we looked at the properties of the material after, from those syntheses. And so you see, very systematic Niels was. We have the limiting current. So the lower the limiting current, the better. And you see that it goes down and has a desirable minimum here at 30% sodium chloride, 60, 70% zinc chloride. The surface area, interestingly enough, goes up through a maximum at exactly the same sort of loading. And it also, there's a salt mixture melting point that goes through a minimum also there. This is a low melting eutectic also. And we think that this is important for the complex colloid chemistry and surface interactions between the salt template and the organic precursors as they melt, as they polymerize, and as they subsequently pyrolyze to incorporate desirable moieties of nitrogen carbon at the surface. Okay, so the high surface area nitrogen carbon results near the eutectic point, and the types of nitrogen species are associated with that are favorable for the oxygen reduction. So why might that be? Well, here's what we think. We think that the difference has to do with the strong electrostatic interactions that are taking place between the same carbon nitrogen precursors in both cases, but in the case of the salt templating, we have strong electrostatic interactions, especially with the zinc. Okay, the zinc is a zinc 2+, and you know that strikes us as being somewhat. Zinc is forming it has these porphyrinic type compounds. I showed this one that I heard a cartoon earlier at the start, where you have these multivalent metal ions that are at the center of these porphyrinic nitrogen-containing macrocycles that basically have oxygen reduction properties. So we think that even though it's at high temperature, these divalent cations in the salt, molten salt, favorably interact with the nitrogen-containing carbon as it pyrolyzes in a very complex chemical way, such that at the surface are these desirable isolated pyridinic groups that basically account for the properties that we have. By comparison, the silica templated, even though we have these nice, beautifully ordered mesoporous silicas, which, you know, coming from Santa Barbara, we thought that not only they're beautiful, we hope they're useful. In this case, they're weak non-ionic interactions principally, doesn't have this propensity to steer the nitrogen to the surface in a way. And we think that the salt templated type materials with these divalent cations are going to be the ones to look more deeply at in order to see if we can favor certain of these nitrogen moieties on the surface for these catalytic heterogeneous catalysis reactions, for electrocatalysis, for not only this reaction, but some of the other properties that I talked about. So with that, I'll summarize by saying this is really a talk about understanding how dilute and disordered functional species in semi-crystalline solids can be understood and controlled and fed back to improve by understanding their sort of key local compositional and structural properties. So they're hard to establish because X-ray is good for crystalline materials, but not very much for these sort of disordered materials. It's very hard to distinguish between nitrogen 15 and carbon 13, for example, or between aluminum 27 and silicon 28, for example, or 29. So, but we can do so by correlating these syntheses, scattering, and especially this two-dimensional NMR with these modeling analyses. And the modeling analysis I'm really appreciative of, because not only does the NMR was helpful, but the modeling analysis gives an opportunity to understand and generalize, and will enable us, I think, to be predictive in kind of the properties that we might want to seek, and then have that being a primary predictive guidance for synthesis. So I think the NMR couples especially nicely to the modeling, and I think that is a partnership with Philippe that we're really grateful for. So we've got new atomic level insights on these macroscopic properties. They're good for oxygen reduction. We are working currently on sulfur reduction for lithium sulfur batteries, which have got similar properties that are desirable. And these are leading to new design criteria for developing materials for these and other diverse applications. So I want to really acknowledge these outstanding students I've had in the group. Shauna, Niels, Zach, and Dong-Hoon are very nice and good friends who become good friends as coworkers from Sweden, UCLA, and Germany. And I'd be glad to take any questions. I want to thank again Adam Schubik and Robert for the invitation. And again, hope to see you all at some point in the future in person to have more direct personal discussions about our shared interests.
Thank you, Brad. Thank you for this great talk. I mean, we learned a lot, I have to say. And I have many questions to you, but I will maybe start first with the questions from the audience. And there is a question from Alexander Jaworski from Stockholm University, my department. So he writes, have the carbon samples been diluted before NMR experiments? In our lab, we usually have big difficulties to tune proton channel under magic angle spinning for such conductive samples. So CP experiments and proton decoupling are very difficult.
Right. Yes. And I may have mentioned that. Yes, we had to dilute it in about at least 1 to 3 in KBr, and for exactly that reason. And the reason is also for the conductivity, but it turned out that it's you may have experienced that yourself. It's really prone to heating under these conditions because you're rotating a conductor in a magnetic field. You get a lot of resistive heating. So the temperature management, that's another reason we did it at low temperature, in part to control the temperature. So yes, we had to dilute it. That further reduces, of course, the sensitivity. And so these are, again, a number of the challenges with doing these types of materials analysis with NMR. But you're right. But it is possible, as I indicate, especially with the enrichment and the high loadings.
Thank you. The next question is from Serhii Butnik. Thank you for a very interesting talk. Could you please give an estimation regarding uniform nitrogen-doped coatings on metallic surfaces by applying chlorine-free eutectic melts?
Okay, so can you repeat that, Adam?
So can you give an estimation regarding the uniform nitrogen-doped coatings on metallic surfaces if you employ this chlorine-free eutectic melts? So,
okay, so I'm trying to, I may not understand exactly the points, but so in this case, so we do have, there's a chlorine there. We do by water leaching pull out essentially everything that's detectable. And we did that with respect to the chlorine, so we think we can pull out those ions quite well. There may be some residual, but even the zinc interactions, which we expect to be strongest, is a very small amount of zinc. So that is largely removed. So the chlorine can be removed. The thing is, these are still kind of powders, so you can compress them. So in terms of coatings, the SBA materials were actually something we intended more for that, because then you can coat them as silica and then pyrolyze it and have ostensibly a carbon coating using the SBA silica. With these salt mixtures, I think it's harder to do that on a surface for a coating per se. But so these, in fact, are powders that we've compressed. So if you want to refine your question based on those responses, please do so. Otherwise, I would be happy to sort of continue the discussion offline.
Okay, good. The next question from Christoph Kopperer from ETH Zurich. Brad, great talk. I did not get why not DNP, because low temperature and KBr should be great for the experiment.
So Christoph, maybe you're right. I mean, we've tried, but we've not been successful in it because of in our hands anyway, and it may be frequency dependent. You've got a 600 megahertz instrument there in Zurich. The carbons absorb microwaves, and so I think my sense of this is that there's even at these low temperatures, there's enough local heating near the point where the low dipole couplings are affected such that we just don't get polarization transfer. So if maybe we can talk, that would be, with Zach there with you, maybe there's something we could even try together if you think there's something that we might do to overcome that. We look pretty hard at that, but just haven't been successful in getting DNP enhancements. Maybe there's ways with using the KBr as an extra boost that might overcome it, but I think it's the temperature problem that is the hardest.
Okay, then another question, but this time from me, Brad. What is, in your opinion, the role of the graphitic nitrogen for the catalysis? Does it have any role, or does it only maybe tailor the conductivity?
I think honestly, Adam, that's a good question. We got a lot of that. I think that is. I think it's unhelpful. I think if anything, it decreases the conductivity. And I think if I was able to direct the nitrogen where I wanted it, where we wanted it, I would put it in these pyridinic sites on the edges where you have the carbonaceous, the graphitic part having maximum conductivity, not being diluted by any sort of defects like a nitrogen in the center of these sheets. But I think at these high temperatures, you get some sort of, it's like musical chairs. It gets just locked in at that point where some of this is in graphitic sites, but I think they're not helpful. I think they probably is what lowers some of the conductivity. I don't expect that they're on the surface unless they're on some sort of surface terrace, but I think the pyridinic ones are on these curved interfaces. And so I think that the graphitic ones are not ones that I think are desirable. That's why I think even though they're more numerous, I think they don't contribute.
Okay, thank you for your answer. Shubik wanted also to ask something. I give the word to him right now.
Yeah. Right. A very pioneering lecture. I thoroughly enjoyed, and you have really taught us how to analyze this solid state NMR. I have learned, but I still have few questions. So I understood like carbon and nitrogen, these positionings that can be possible to answer. But my question is, how about if you have heteroatoms for say fluorine, trifluoromethyl group, or phosphorus or oxygen? Can we also be able to predict where is the location or?
So what's nice about these particular experiments is that, yeah, and NMR in general is that, as Christoph knows and others, is that and atoms that you know, most of the periodic table has an NMR active isotope. There's very few elements that don't. Things that the ones that you just mentioned are really good. The fluorine and the phosphorus anyway, those are 100% natural abundant. Spin 1/2, like each of the two atoms that I mentioned here, that nuclei I mentioned here, they would be particularly suitable. Yeah, so I think oxygen 17 and sulfur, for example, we're interested in sulfur. Those are very hard. They're very dilute. They're quadrupolar. They have very low gyromagnetic ratios in the case of sulfur, especially. Those become more difficult. If we or Christoph are able to get perhaps dynamic nuclear polarization working, that might be one option. Again, but we're kind of limited by some of the difficulties of these conductive systems, which is why they haven't been studied at this point very much before. So I think that, but some of those you mentioned would be really good candidates.
Okay, thank you very much, Brad.
Good. Robert, maybe I give a word to you. I saw your hand, please.
Also, my question would be rather regarding applicability and in which pH and temperature ranges these materials can be applied, and in which devices finally.
So the ones we've been using, so what I showed here were under acidic conditions for the oxygen reduction. It also works under under conditions of alkaline conditions. It's and what I didn't show, but we've tested this on some actual fuel cells with our coworkers down in the lower right-hand corner at Teledyne. It's a company down in Southern California, and they've incorporated these into actually a functioning alcohol fuel cell. And in this case, on the cathode, it's actually far more stable to poisoning and crossover of alcohol kind of fuel sources, because these carbon sources, these nitrogen carbons are not deactivated or otherwise adversely affected by alcohol in terms of their use in fuel cells, unlike platinum. So I think that the stability of these and the low cost makes them something that I think now can be, with the understanding and the feedback, I think we can tailor them to the kind of things that I think are these fuel cells. Okay, that's pretty clear. We're working with the group UCLA, and especially Shongfeng Duan there in the center. He's an expert on lithium sulfur batteries. Not to look at the sulfur because that's not high, but it turns out that we can do the same type of measurements, show that we have similar dependencies. It's this and desirable properties for lithium sulfur batteries that are also better for the salt templated than the silica templated one, but with different nitrogen contents. So we expect there may be some different nitrogen sites that may be actually important for the sulfur reduction. The other thing that I think is for supercapacitors, because supercapacitors with the mesoporosity is a way you can actually, you need to get ions inside, you need to have bigger pore spaces. We've not looked at that at all, except to just sort of realize that this is probably a way to promote, some sort of hydrophilicity, which would be for some of these double layer capacitors. And then coming from Arizona, and California is becoming a de facto desert as we speak. I think water treatment is another one which this is going to be useful for, because of the ability to have the control over the surface chemistry in a more sort of favorable way for pulling out organics and even perhaps inorganic species from the purifying water. So those are the application areas that I think are maybe useful for some of this. And I expect they would have different surface chemistries, different additives, maybe sulfur, maybe phosphorus dopants, from which then to basically improve it. I don't think it's necessarily have to be nitrogen, but I think the way that we're studying it could be appropriate for all of them.
Okay, thank you for the answers, Brad. I would have one question which is directed to you and also to Paolo directly, because now we saw, Brad, in your talk, a kind of atomistic understanding of heterogeneous catalysis, and Paolo made a lecture on homogeneous catalysis. So where do you two see the future of both kind of directions of catalysis, which they interact more with each other, or what can we learn into the future?
Well, I've got an opinion, but Paolo, do you want to go? You want to go first?
If you have already an opinion formed, I think you can go. I think that will be in the future probably contact points should be something that can be positive for both fields. But I'm curious to know what is your opinion.
So, you know, it's I think we've got one of the world experts on listening in, which is really flattering. Christophe Copperet is kind of one of the, and others are really seeking to do these single site catalysis. And I think the challenge for me is to take the elegant chemistry and the molecules that are being developed by our homogeneous catalytic colleagues like Paolo and the many others in the chemistry side, and somehow be able to impart them onto these heterogeneous surfaces. And so Christophe is really one of the world leaders in that. And there's others where you understand and define that site very well. Like I said, we'd like to have isolated pyridinic. We're not good at necessarily yet at this point making most of the material isolated pyridinic sites and leaving all the other stuff away, because all the rest of it is waste. At least in this case, it's an isolated nitrogen. It's a nitrogen site. And so if we have graphitic nitrogen, we don't really care. It's not really costing us much. If it's platinum or rhodium or indium or something like that, it's really valuable to be able to put it where you want. So I think it's this single site catalysis that is really, really brings these two fields of homogeneous and heterogeneous catalysis together.
Okay, good. So yeah, thank you all for these answers to the questions. So I also have learned a lot regarding NMR. So it's a big field. With this, I would like to thank you and Paolo again for being here today as our guests. We enjoyed it very much. I also would like to thank our attendees who are here with us, which make this event possible. And with this, I think we come to the end of our third lecture series. So again, thanks a lot. And yeah, I hope we can meet each other very soon in person when the situation settles.
Hopefully so. Thank you very much for the invitation. It was really great. Thank you.
So,
yeah, thank you both all for your initiatives in organizing these. This is really a helpful service to the whole community globally.
I agree, absolutely.
Yeah. Good. With this, I would then close the session and see you hopefully the next time soon. Yeah. Thanks
Bye-bye.
again.
See you soon. Thank you.
Bye.
Bye-bye.
Bye-bye.
Bye.